Thanks, Ursula. I'll share my screen.
Perfect, and I'll give you the 1 minute. I haven't been able to because people are so on time.
Okay, thanks. And thanks to the organizers. So I actually sort of narrowed the talk subject to our recent simulations that include jets around the companion in a common envelope setting. So here's our group. Well, actually, we've arguably we could add more people to here because we've worked with other groups as well. But these are the people who are involved in this, who have been involved in the common envelope simulations. And our simulations are basically, these are the basic parameters. So we have pretty high resolution. We use adaptive mesh refinement. The code is called AstroBear. So far, the ones I'm going to be talking about today have an ideal gas equation of state with gamma 5/3. And we modeled the companion using a particle like other groups. The primary star is set up using MESA and basically the method of Ullmann 2017. And so we have a particle replacing the core as well. These are the papers that we've done so far involving simulations. And the one I'm going to be focusing on today is the last one. Amy is the first author, and she is also in the audience if you have questions. She also gave a talk a few weeks ago on this work, and please check it out, the CIPO conference. Okay, and here is basically the simulation without jets that we're going to be comparing to. This is a 2 solar mass RGB star. So all our simulations in this work were with the same primary star and same secondary. Well, actually, no, a couple were with a smaller secondary, but most of the ones I'll be talking about. And it lasts for 40 days, about 10 orbits. Here, I'm just showing the red is the unbound mass, the blue is the bound mass. This is in the orbital plane, sliced through the orbital plane. The dots at the center, the purple dot is the RGB core, the red dot is the companion. It's a point particle, so it could be a main sequence white dwarf. And the yellow is the density contours. Okay, so we added a jet, and our jet model is something like this. So we have 2 spherical sectors with their axis perpendicular to the orbital plane. And in those spherical sectors, we add the jet material at a certain rate. And this is all within the softening sphere of our particle. So you can think of the particle mass as being smoothed out over this, not evenly, but extending up to the edge of the softening sphere. The resolution element is shown here. And we did several runs. So the first run is our fiducial run. We modeled the jet for a main sequence star of about a solar mass. Our companion is about a solar mass. Our m dot jet, so the amount of mass we put into the jet, the rate, is 2 × 10⁻³ solar masses per year, which is quite high. It's the Eddington rate for the sun, essentially. So it's kind of an upper limit in some sense for a jet, because normally the accretion rate, you'd imagine, could be a bit higher than Eddington, and the jet mass loss rate would be some fraction of that, but we set the jet mass loss rate. We do not tie it to the accretion in this paper, at least. The accretion rate in this case is actually 0 for this particular run. And then we remove mass from the point particle companion at the same rate as we injected into the jet to conserve mass. Our jet velocity is twice the escape speed, 864 kilometers per second, and our half opening angle, 15 degrees. Then we try to run where we don't remove mass from the companion, just to make sure that there's no big difference, that the amount of mass is small anyway, and sure enough, there isn't a big difference. Then we have a run without a jet. We repeated the run from our past papers to make it identical to the jet run, but except for it doesn't have a jet. We have one with twice the velocity of the jet. We have one with twice the opening angle. We have one with now accretion. Okay, so now we added accretion in the same way that we did in our 2018 paper. Now it turns out that the accretion is much higher than it's the Bondi-Hoyle-Littleton accretion. That's what the code does. It's the Krumholtz 2004 model. but it turns out it's much, much higher than Eddington, probably unrealistic, so considered an upper limit to the accretion rate. And this J4 is like our fiducial, but includes that accretion. And the accretion is shown down here as a function of time for the different models that include accretion. J5 is our most extreme parameters, where we multiply the m dot jet by a factor of 10. Then we have the half mass companion. We tried that as well. And then finally a white dwarf parameters. So the jet now has, so the Eddington rate is now 100 times smaller roughly, because it roughly goes as the radius, and the radius is about 100 times smaller for a white dwarf. However, the velocity roughly is proportional to the escape speed. So the escape, so it's about 10 times higher. So the jet power, m dot v squared, is roughly the same, but now most of it is because of the velocity, right? So this is more like a white dwarf. So that's the last model. So basically here, I just wanted to show a low resolution test run to point out that our model adds mass. It doesn't subtract mass from the envelope. It doesn't remove anything. It just keeps adding. And it actually takes a while. On the top row, you can see it takes some short amount of time to accelerate the ambient gas around it up to the jet velocity that we put into the model. And so, yeah, and then it takes a bit of a longer time to actually add enough mass to get the density that we would expect from the jet if we just do a simple calculation of m dot using m dot and the jet velocity. And basically at that same time as the density becomes its final value for the jet is starts to advect out of the jet launch region, right? And this is based on the model of Federath 2014. So here's the movie showing a slice through the secondary, which is at the center. The softening radius is shown there. And it's perpendicular to the orbital plane and perpendicular to the line, to the imaginary line joining the primary core particle and the secondary. And on the left, you see just the jet material. So we have a tracer for that. And then on the right is all of the gas with the velocity vectors. So you can see that the jet starts off strong, as it should. It's basically vertical right there, and then it deforms, becomes unstable. It starts bending in like a sideways V shape. The velocity is towards the left, so like a backwards V, and then it it basically chokes and ends up, the jet material ends up in a kind of a quasi-spherical region at the center where you have very high envelope density. And the density, the color is the same in both plots here. Okay, so then you can look at that more frame by frame kind of thing. And at the beginning, you see that it's nice and vertical. And I'm showing the separation curve on the bottom here for the no jet run and our fiducial jet run. So this is all for the fiducial jet run. And you see that it deforms and it basically quenches. It quenches around the time of the first periastron passage, so pretty early in this evolution. And you see that by this time, the density of the jet is very subdominant compared to the density of the envelope gas. Okay, so you could actually compare the no jet and jet runs. So early times, and this is a different slice now. This is a slice through both particles, again, perpendicular to the orbital plane. But you can see a difference at early times. Once you get to just before the periastron passage, first periastron passage, the differences become less obvious. And you can see in the jet run, you do see this shock structure. Okay, so this is interesting, and it shows that the jet is beginning to get choked. And then finally, around the time of the first periastron passage, it's very hard to even tell the difference. Now, it's important to compare with the literature, because there was an interesting paper by Schreiber et al. I don't think Sagiv is here at the meeting, but other authors are here. And they also see the bending that we see. In this case, there's a similar slice, but it's going to the right, the secondary. And they see the choking of the jet. And you can see that the jet here cannot, it's confined. So in this part, we agree. However, after their jet is choked, they find that it eventually breaks out again along the polar directions. And so do we find this? So first of all, for a fiducial model, like I showed you, we don't see any of this. We don't see it breaking out again. In fact, it's completely subdominant, both density-wise and energy-wise, because this is grid-based, so everything else, temperature and velocity and so on, is property of the grid. So it's property of both the jet gas and all the gas that's co-spatial. So really, you can just look at the density, and if it's subdominant density, subdominant in energy, at least in our code. And so it's basically as if it's not there. It's still injecting energy at the same rate, but it's not doing anything much. And so, but if you go to our model with accretion, J4, it's the same as the fiducial, but it has accretion now. Remember, this is a very high accretion rate, about 100 to 1,000 times Eddington for main sequence star. But you see that the jet starts to reemerge at the end of the simulation. First, it reemerged in the upward direction, and then finally in the downward direction, and that's the final snapshot that I'm showing. And so, but this isn't really breakout. It's not breakout because it's still completely subdominant compared to the envelope gas. Again, this is the same color bar for both rows.
1 minute.
Okay. And actually the reason, so it's, the other thing is that the gas, even without a jet, in a pure accretion run, the gas flows down or up through the torus, and not all of it will accrete at the center, and so it will keep going because of the momentum. So it's sort of a random flow through the torus, and that's more of a product of the accretion than anything to do with the jet. So the jet gas gets entrained actually by the flow. And even for our most extreme parameters, now the jet is sort of marginally breaking out because the density is comparable, but still not really breakout. If you look at the mass unbinding, it's so this is the unbound mass as a function of time. We use this criteria, slightly different from what other people have used. But you see that for all the runs are plotted here, including the no jet run, very similar. And on the bottom is the residual, the difference between the jet runs and the no jet run. There is an enhancement of a few percent overall, and up to about 20% or 30% at early times. That this pink one is the double velocity jet run. Okay, so at early times, you do get about a 20% enhancement in the unbound mass. And these numbers are comparable to the jet power divided by the rate of orbital energy release. So kind of predictable in a sense by theory. And these are for the accretion runs, and you get slightly higher unbinding. You also see that for J8 and J4, J4 have the same power, but J8 has a higher velocity. It's the white dwarf run, and you see that actually helps you more. So the velocity matters more than the m dot for equal power jets in terms of unbinding at early times. Okay, so I'm just put this quickly. So I do want to say that in the Schreiber paper, they claim that 3 times as much envelope mass is unbound compared to the no jet run, but they have a very different way of calculating the unbound mass from us. So we look at all the mass in the simulation, and they look at the mass outside of a sphere of 1 AU radius. And you can ask, okay, well, our simulation is short. What would happen in the long run? And you can estimate how long it would take for the jet alone to unbind the envelope. And you have to assume some efficiency and so on, but I get a number of 50 years for these optimistic jet parameters. So it could be important, but it probably wouldn't be dominant compared to the orbital energy, because most people estimate common envelope phase would take about 10 years for this particular system. So I'll leave my summary up, and thank you very much.
Thank you, Luke. Miguel?
Yes. My question is about the way your criteria for unbound mass. I noticed that you have 3 different potential energies, and I noticed one it was 1, 2, and self. Yeah, not in the next one.
Yeah, sorry, I skipped it.
Yeah. So can you elaborate a little bit on that criteria?
Sure.
Please.
Yeah. So the potential energy. So the self is self-explanatory. So it's just the gas with itself. The other 2 are the gas with the particles. So so half of that is nominally, half of that potential energy is nominally inside the particles themselves, and half is in the gas. Now, particles are really just gas in reality, but in our simulation, they're particles. So we actually, this integration is, or these energy densities are just talking about the envelope gas, right? So, but to get the full interaction, the full potential energy between the particles and the gas, we have to include the part that's in the particles. That's why we multiply by 2. But I mean, it's pretty arbitrary. We can do it without those factors of 2, and you don't get a big difference. I've tried that.
I had a similar issue last week about that, how to define that, because that factor of 2 for me, it changed some things. Thanks. And if I can make one more question, it's about how do you find your thermal energy?
The thermal energy is just it's just the total energy minus the kinetic energy, the bulk kinetic energy. It's the total energy without, sorry, total energy not including the potential energy. The total energy as defined, the energy as defined in these codes, right? The Astrobear code, the Riemann solver, it's energy conserving, but it doesn't, but then the gravity is modeled with source terms. So you have this E, which is just thermal and kinetic, bulk kinetic, and then we just subtract the kinetic to get the thermal.
All right, thank you.
Sure.
Luke, what about the criticism that all people who do jets in common envelopes get, that there is no such a thing as an accretion disk inside the common envelope? So these were from papers from Morgan McLeod. And so it'd be difficult to launch jets in the first place, even if you're accreting in some manner.
Well, I'm not sure which paper. I don't know which papers you're talking about. Well, I remember there was one paper in Morgan's group where they do find that there can be disks in the common envelope, that by I forget the first author's name, but so I'm not sure that's known, but this is a very simple first step where, like your paper with Sagiv, where we assume that there's accretion and we assume that there's a jet and we just put it in. But yeah, we need to link, in my last slide I had that mentioned, but I didn't have time, but we have to link the jet and the accretion better. So right now we have them separate, but really what we should be doing is have a more realistic accretion model that caps the accretion rate at some, the Eddington rate or something, maybe 10 times the Eddington rate, and then have the jet, the mass loss rate, be some 1/10 or something of that. But yeah, so I'm not sure we really know what happens in terms of accretion inside the common envelope. But we can try putting that in more carefully in the future.
No?
Yes, very impressive simulations. Just general comment, when we talk about common envelope with jet, we need to, I think, examine 3 types of stars. One is black hole neutron star, which I expect them to launch very energetic jets. The second group is white dwarf, which I do not expect to launch any jets, because if the accretion rate is high, it will start burning, nuclear burning, and will be a core by itself. So it will be an AGB star, RGB with 2 cores. And then there is a main sequence. The main sequence, you are right, in the inner region of the envelope, I don't think the jets will do much. And there is a paper today on AstroPH, which I put on Slack, not mine, that comes to the same conclusion. So I think most of the influence of the main sequence star with jet is while it is outside the envelope in a Roslob overflow, or when it comes closer in what they call the grazing envelope evolution. And there, this is a stage where we should look for the influence. And Sagiv Shiber mainly with me did simulation when the companion was quite outside in the envelope. But now in the new paper, which with the Mexican group is come to the conclusion, A, that the jets do not go out, and B, that it is very hard to form an accretion disk inside the envelope. So when the main sequence is outside the envelope, just grazing it, I think it's an accretion disk will be formed, like in post-AGB star, where the orbital period is 100 to 300 days. And this is where main sequence companion with the jet can help unbind the envelope. And it might explain earlier talk about the difference of planetary nebulae of single degenerate, meaning main sequence companion, or double degenerate with a white dwarf companion. And I think this might also account for that. But yes.
Yeah, thanks. I saw that paper last night when I was going through archive, and that's exciting, and we can definitely, I need to read that. Yeah, so I think we do find that more unbinding happens. I mentioned that 20 to 30% right at the beginning before it plunges in. And that is the very early phases when it's just around near the surface of the envelope. And at that point, this is comparable still to E dot, the jet power divided by the rate of release of orbital energy, because it's not falling in very fast at that point. It's just getting started. So we do notice more unbinding there, but the plunge in then happens very quickly because you get an accretion stream, and it's hard to avoid that, I think. So we don't see a real grazing phase, but we do agree that there's more accretion, more unbinding from the jet early on. And the neutron star that you comment about, yeah. So my last point here, I do think from our analytic estimates that the neutron star can accrete, and a jet from the neutron star would make a huge difference, because you can have hyper critical accretion much higher than Eddington, some 10 to the 4, even 10 to the 6 times Eddington, so that your jet power could be similar to a main sequence star, but your velocity could be like 1/10 of the speed of light. So it can have a huge effect. And our estimates suggest that it may not even get choked in some cases. Even if it does get choked, it's depositing energy at a faster rate than the orbital energy. And so it can be very interesting. So the reason we haven't simulated it yet is because with these high jet speeds, well, aside from relativistic effects, but even without that, even if you could neglect that, it's just the time step gets so short, right? Because the speeds get so high. So it takes more computing power, but that's a next step.
Yes. So we cannot do it with the velocity of the 100,000 kilometers per second. So we assume mixing already near the neutron star and inject it with more mass and lower velocities. Otherwise, the computer cannot handle.
Okay. Mm-hmm.
Thank you. Thank you, Luke.